Okay, hopefully last video for the day. We have a change in momentum. Okay, a large change in momentum means that we have a large impulse. Okay? And momentum is mass and velocity of an object. We see a large change in momentum in a car crash, right? We go from having a lot of velocity and a lot of mass, and then it goes to having no velocity. It comes to a stop, and the mass remains constant. And so that's a big change. So our final momentum is actually 0 because the velocity was 0, but this change here, it's still a large initial that has to end at 0. So we have a large change in momentum, which will result in a large impulse. Okay. So let's continue to discuss this. Our starting velocities are going to be the same. I'm going to write this up above. I'm just going to lay out the momentum being the mass of the car, velocity final, minus mass of the car, velocity initial. We have some initial velocity. Okay. Our initial velocity, that might change. And this should make sense. Like if we have a small initial velocity, then this change in momentum is small, so the impulse is small, so that would mean the force of that would be small on you or on the car, right? But if we have a large initial velocity, then that's a big change in momentum, which could result in a large force on the car or on you. And so we use this science to help protect and make predictions and design safety features within vehicles. So here's my question for you. Look at these two situations. Okay? Everything's identical as far as the car and the initial velocity, and they're both eventually going to come to a stop. So their final velocity will be 0. But which car would you rather be in? And why is that? Okay, so which car is the driver less likely to be injured? And why would that be? If the velocity is the same and the mass is the same, so that initial momentum is the same, then why is it that we would rather run into a haystack versus a brick wall? Okay? Okay, think about that for a moment. I want you to write down an answer. Okay? Right here below. Give me an idea. Make a prediction, and then we'll talk about it. Okay? Making that prediction. Thinking through the momentum and impulse theorem, which we had up above there, right? Maybe so you can still see what's happening here. So we know impulse, which is a force over a time frame, is the same as momentum final minus momentum initial. Okay. Now, in both situations, this change in momentum is the same, right? The initial velocity is the same. The mass is the same. Let's see. The initial velocity is the same, the mass is the same, the final velocity is 0, and the mass is the same. So this component is the same in both situations. But there's something interesting going on here, and it's the interaction between these two. That the force acting on the car or the person in the car in this situation is small because the time it takes for this force to be applied is big. Okay, so here in this situation, the force is small, but that amount of time the force is applied, doing little t, is big. And so there's less of that force impact on you and on your vehicle. But on this one, the amount of time that force is being applied is really small, so that force must be really big then. That must mean we have a really big force over a small amount of time, so that we have the same change in momentum. Okay? So if we can extend that time where the change of momentum is the same, then that results in a smaller force. Smaller force, less damage. Let's go over a common misconception. Which has greater momentum? Which is harder to stop? A semi-truck going 2 meters per second, or an elderly couple walking down the road going 2 meters per second? Which one would be harder to stop? Well, I would think the elderly couple. And in the thought of momentum, why would that be? Momentum is mass times by velocity. The mass is so much greater, and so to change that momentum to 0, it's going to have a larger change in momentum. We're going to have to apply a greater force or a smaller force over a longer period of time than it is for something that is less massive. Okay? So the common misconception here is that anything that has the same velocity has the same momentum, and that's not the case. Mass is a big part of that. Okay, last item for today, we're going to end with an example problem, and then you'll be working on the assignment. So we have a 22,000 kilogram vehicle traveling at 26 meters per second can be stopped in 21 seconds by gently applying the brake. It can be stopped in 3.8 seconds if the brakes are slammed on, or in 0.2 seconds if it hits a concrete wall. Okay, so 21 seconds by gently applying the brake, 3.8 seconds if the brake is slammed on, 0.22 seconds if it hits a concrete wall. What is the average force exerted on the vehicle? So let's list a couple things we know first. We know the mass of the object. So the mass is 2,200 kilograms. We know that the velocity initial in all situations is 26 meters per second. The velocity final, which you may not have picked up on initially, that's going to be 0, right? Because it says it comes to a stop. Okay, great. The other info we know is the time component, how long it takes for the object to come to rest. And in the first situation, it's 21 seconds, and then 3.8 seconds, and then 0.22 seconds. Okay? So we will know the time. There's 3 of them there. We'll call it situation 1, 2, and 3. That'll be easiest. So time, situation 1 for time will be 21 seconds. Situation 2 for time will be the 3.8 seconds. And situation 3 for time will be 0.22 seconds. Now let's grab that impulse momentum theorem and let's use that. So we know that impulse, which is the net force multiplied by the time that force is being applied, and that's going to be momentum final, which is mass velocity final, minus momentum initial, which is mass velocity initial. Okay? Now, in each situation, that final velocity is equal to 0. So that component is 0. And anything multiplied by 0 is 0. So this whole component's going to drop out. So we will have force equal to negative, or sorry, force being applied over time, so impulse is equal to negative mass velocity initial. Okay, and we're solving for this net force, right? The question is, what is the average force exerted on the vehicle? So we'll divide by time, we'll get it by itself. Sorry, it keeps focusing and refocusing. Let's see if we can. Hopefully that helped. So let's get it by itself. We'll divide by the time component, the delta t. So force is equal to negative mass velocity initial divided by delta t. And now I'm just going to start plugging in numbers for each situation. Okay, so I have a time 1 situation. So we have on the top of our fraction, we have a negative, and that's multiplied by the mass, which was 2,200 kilograms. And then that initial velocity was 26 meters per second. So there's the top of the fraction divided by the bottom of the fraction, and this is the time 1, so that'll be 21 seconds. So the first net force being applied, negative 2,723.81 newtons. It's a lot of numbers. Let's look at sig figs here. 2 sig figs, 2 sig figs. Okay, so it looks like we're working with 2. So the force in the first situation would be negative 2,700 newtons. Does the negative sign make sense? Where are we at time-wise? Okay. We have an overall negative force, which means the acceleration is negative. So if that velocity was positive, a negative acceleration would cause the object to come to a stop. So that makes sense. So good with that number. Now what about in time situation number 2, where we have a little bit less time, we're slamming on the brakes. Everything else stays the same. I'm just changing the time component, so now it's 3.8. So that is 2 sig figs negative 1, 5. So that is 15,000 newtons, so it's a lot more force. And then time 3, let's see how much force we're going to have if we hit a brick wall. So that's 0.22 seconds. And that was negative 260,000 newtons. Okay, so we have a huge negative force, which means a huge negative acceleration, a little bit less, a little bit less. So the longer we take to stop, the less force and that thus acceleration that is going to occur. All right, guys. So now we're just working through that assignment. Okay.